Okay, so let's get started. We're going to be taking a look at understanding the differences between our air fuel that you'd see on a wideband gauge, units of lambda, and what fuel stoichiometric is going to actually represent here within the Motec. These are all related and they're also mixed together a lot of times, and it's a very kind of confusing topic for a lot of people as they're starting to calibrate and tune within a VE style or airflow modeled system. Let's jump in here and try to break this down and understand what's going on here. So when we're talking about lambda, as we'll find in our target lambda table, these values may not be something you're familiar with. If you're used to looking at a wideband gauge, wideband gauges are almost always going to read in default units of petrol air fuel. 14.7 to 1 would be stoichiometric, and something like 12 to 1 would be richer, and then something like 18 to 1 would be leaner. So a lot of people are more familiar with those petrol air fuel units, but there's a huge advantage to tuning in units of lambda as what we find here in our target lambda table, or what the actual native units that we're going to see expressed with our exhaust lambda sensor. That's going to be coming from our wideband. That's going to register and read. Everything is going to be natively based around units of lambda. We're going to talk about why that's really, really important, but let's understand how the target lambda here, or units of lambda, tie together within the programming here. So first thing I want to talk about is going to be our fuel Stoich, because that's something we have to get out of the way right off the bat. We have to program that correctly based on the fuel that we're actually using in our fuel system for tuning our engine. If we jump here from our tuning page and we jump down here into our setup and we go here under our basic setup, we're going to find here under fuel properties Stoich ratio. This expresses the stoichiometric ratio of the fuel that we're dealing with. Now, within the airflow and fuel modeling with the Motec, we're going to find we have an underlying equation. Fuel mass is equal to air mass divided by target air fuel. Now, the air mass is calculated based on knowing map pressure, charge temperature, which is a function of engine coolant temp, and air inlet air temperature. We also know volume per cylinder, and then the percentage of volumetric efficiency coming from our VE table here. So knowing all of that information, we'd know the air mass, which is going to be called engine load here in the Motec. When the engine load is known, we also then need to know the target air fuel. Now, target air fuel will always be the fuel Stoich that we program, so based on what type of fuel we're working with, multiplied by our lambda from our lambda aim table here. So this is the desired lambda multiplied by the fuel Stoich will give us target air fuel. Once we know engine load, we know target air fuel, it's just going to be engine load divided by target air fuel gives us fuel mass. Now, fuel mass gets converted into an injector pulse width based on knowing the properties of our fuel. That's going to be the density and the temperature, also knowing the volume flow of the injectors that we're dealing with, plus looking at the fuel pressure if we actually have that fed into the Motec. And then we add in any of the injector data, which would be the latency and the short pulse width tables. That'll give us an actual pulse width that we deliver to the engine, and that if everything is set up right, so we're expressing the correct engine load or air mass, and we have everything modeled correctly on the fuel mass side of things, whatever our target lambda here is going to be is what we'll actually see at the engine. So we look at our exhaust lambda, we should see that that's going to register and read what we have here in our target table. That's assuming everything is calibrated perfectly. That's usually not the case, and we have to do some actual tuning, so that's where things come in when we do our calibration side of things. But understanding how fuel Stoich and lambda fit together are important. Now, here's where a lot of people get really confused when they're looking at a wideband gauge and then looking at this lambda aim table or units of lambda. They're going, what the heck is going on here? How do I convert or work with units of lambda? That's actually really simple. And I have an Excel spreadsheet from our course that's going to make a bit more sense of this. You can actually punch some numbers in and see how everything's going to fit together and the advantages of tuning in units of lambda. Let's jump and take a look at that calculator here. So jumping into our Motec M1 course calculator, I have a page here labeled Stoich. What we're going to find is that we have our values here in the blue. These are things that we can change. And whatever we have here in the green, these are going to be a calculated value. Now, the reason why I have this set up here in this fashion and having petrol, air fuel, ethanol, methanol, propane, methane, hydrogen. These are fuels that we could potentially burn in our engine. We're going to find that all of these fuels have a specific Stoich value of what's going to be the ideal portion of air and fuel to get to the ideal torque output, emissions output from the engine. That's what's known as stoichiometric. We're going to find that they're all tied together with units of lambda. So, tuning in units of lambda, we do not need to know anything about the fuel Stoich of the fuel we're working with. We can, if we want to run at stoichiometric, we can just type in 1.0 lambda right here, and that'll give us on petrol air fuel 14.7, ethanol 9:1 air fuel, methanol 6.45, propane 15.67, methane 17.19, and hydrogen 34.3:1 ratio. If we want to go richer, so let's say we're getting up into boost and we want to richen up our mixture, we would go with a lower lambda number, and something like 0.78, 0.76 lambda is going to be sufficient for forced induction engine under boost. Let's type in 0.77, kind of split the difference. If we click enter, what's going on?
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here. And you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.